All right, team. Gather around for a few minutes. Today we're going to cover unbonded capping systems, one of the most efficient ways to prepare concrete cylinders for compressive strength testing when it's done correctly. Now, I want you to look at the diagram on this first page. You're seeing a concrete cylinder sitting inside a metal retainer with an elastomeric pad, usually neoprene, between the cylinder end and the machine platen. That pad is what helps us achieve a uniform load transfer without grinding or sulfur capping. But let me be very clear. Unbonded caps are not easier. They are faster, yes, but only if we follow the rules. If we don't follow the rules, we will create bad breaks, wrong strengths, and safety risks. Today, we will walk through where unbonded caps are allowed, the safety risks, the pad and retainer requirements, how to prepare cylinders, how to run the test correctly, how to track pad reuse, and when qualification is required. By the end, I want every technician here to be confident enough to set up and run this test properly, and also to know exactly when to stop and say, "This specimen cannot be tested as is." Now, I have two questions for you. What do you think happens if the pad is too soft for a high-strength cylinder? Why do you think we even need the metal retainer ring? Now, let's talk about where unbonded caps are allowed, because this is the first place technicians make mistakes. Look at the bar on this slide. It's showing 3 zones: prohibited, low strength, roughly 0 to 10 megapascals; allowable, standard range, roughly 10 to 80 megapascals; restricted, qualification required, roughly 80 to 100 megapascals. So what does that mean in practical lab terms? If your concrete is too weak, the pad system is not reliable because the specimen may crush unevenly, and you may not get a representative failure mode. In the middle zone, 10 to 80 megapascal, this is the standard range where unbonded caps are commonly used. Above 80 megapascal, you're entering higher energy failures and higher sensitivity to alignment and pad stiffness. That means qualification is required. Also note the specimen types and sizes listed. Hardened concrete cylinders, standard sizes like 150 by 300 millimeters and 100 by 200 millimeters. And the slide also reminds us of the pressure equivalents. 10 megapascal, approximately 1500 psi. 80 megapascal, approximately 12,000 psi. So when someone hands you cylinders and says, "Just test these," your job is to first ask, what strength range are we expecting? Because pad hardness selection depends on that. Now, a few questions for you guys. If a mixed design is expected to hit 9 megapascals, should we use unbonded caps? If we're expecting 85 megapascals, what is the first thing we must confirm before using pads? Team, this slide is not optional. This is the slide that keeps people safe. When we test cylinders with unbonded caps, the failure can be more violent than with bonded caps. Why? Because the elastomeric pad stores energy during compression, and when the cylinder fails, that stored energy can release suddenly, almost like a spring snapping back. That's why you see the warning, stored energy release. Look at the illustrations. A bonded cap break is typically more predictable. An unbonded cap break can eject fragments more aggressively. So our safety rules are: the compression machine must have protective enclosures or heavy-duty guards. No technician should be leaning in line with the specimen during loading. Keep hands clear, face clear, body clear. Always assume the cylinder may burst. This is also why we don't allow casual spectators near the machine during testing. Now a few questions. Where should you stand during loading? Directly in front of the cylinder or offset to the side? What do you do if the guard is missing or not working? Now let's focus on the pad itself, because the pad is the heart of the unbonded system. The material is typically polychloroprene, which is neoprene. If you use alternative materials, the slide makes it clear. Full qualification testing is required. Now look at the dimensional requirements. Pad thickness is shown as 13 plus or minus 2 millimeters, about ½ inch plus or minus 1/16 inch. That thickness matters because it controls how the pad deforms and spreads load. Also, the pad diameter must fit properly. It must be slightly smaller than the retainer ring inside diameter. The slide indicates the diameter must be less than 2 millimeters smaller than the retaining ring ID. Why do we care? Because if the pad is too large, it can bind or buckle. If it's too small, it may not cover the full bearing surface properly. So the technician's responsibility is: verify thickness before use. Confirm the pad fits inside the retainer cleanly. Confirm it seats flat with no curling. Now, a few questions. What happens if the pad thickness is out of tolerance? If the pad doesn't sit flat in the retainer, do we test anyway? This slide is one of the most important operational slides in the entire deck. Pad hardness selection. We select pad hardness based on anticipated concrete strength. The hardness is measured in Shore A durometer. Here's the matrix shown. 10 to 40 megapascals, 1,500 to 6,000 psi. Shore A 50, max 100. Uses 17 to 50 megapascals, 2,500 to 7,000 psi. Shore A 60, max 100, uses 28 to 50 megapascals, 4,000 to 7,000 psi. Shore A 70, max 100, uses 50 to 80 megapascals, 7,000 to 12,000 psi. Shore A 70, max 50, uses. Now notice something. Once you get into the higher strength range, the pad reuse limit drops from 100 down to 50 uses. Why? Because higher strength concrete creates higher stress on the pad, and the pad wears out faster. So the technician must do two things: choose the correct pad hardness, track the reuse count, and retire pads on time. Now a few questions. If you use a Shore 50 pad on a 70 megapascal cylinder, what type of error do you expect? Why do you think the reuse limit drops at higher strength? Now, let's talk about the metal retainers, because pads alone don't solve alignment. The retainer is what controls pad confinement and stability. The slide shows the inside diameter, ID, of the retainer should be approximately 102% to 107% of the cylinder diameter. That means the cylinder should fit inside with a little clearance, but not too much. The retainer height is shown as 25 plus or minus 3 millimeters, about 1.0 plus or minus 0.1 inch. And we have minimum thickness requirements depending on retainer size. For 150 millimeters, 6 inches retainers, wall 12 millimeters, base 12 millimeters. For 100 millimeters, 4 inches retainers, wall 9 millimeters, base 8 millimeters. Also notice the plainness tolerance shown, 0.05 millimeters, 0.002 inch. That is extremely tight because the retainer base must not introduce tilt. So your inspection points are retainer ID and fit, retainer height, retainer base flatness, no dents, no warping, no cracked welds. Now,
A few questions for you guys. What happens if the retainer base is not flat?
If the cylinder is loose inside the retainer, what kind of failure pattern might we see? Technicians, this is where quality control starts. If the cylinder ends are not acceptable, unbonded caps cannot fix bad geometry. This slide shows two rejected conditions. 1. Perpendicularity error. The end must not depart from perpendicularity by more than 0.5 degrees. The slide notes that's about a 1 millimeter slope in 100 millimeters. In other words, the end can't be tilted. 2. Surface profile error, depressions. Depressions must not exceed 5 millimeters, 0.20 ends. So if the end has a deep gouge, a honeycomb pocket, or a damaged corner, the pad will deform into it and you'll get an uneven load transfer. The action statement is clear. Cylinders failing these checks must be sawed or ground prior to testing. So your job is to inspect the ends before loading. Do not hope it passes. We test correctly, or we don't test. Now, a few questions. If the top end has a 6 millimeter depression, what do we do? Why does end squareness matter so much for compressive strength? Now we are in the hands-on part, setup. This slide shows a simple 3-step flow. Step 1. Inspection. Check pads for cracks or wear. Verify pad dimensions match the retainer. This is where you look for cracks, splits, hardening, excessive scuffing, deformation. Step 2. Dusting, optional. Apply cornstarch or talc to prevent sticking. This is optional but very helpful, especially when pads are new or when the surface tends to grab. The key is a light dusting, not a pile of powder. Step 3. Assembly. Insert pad into retainer. Ensure it seats flat. This is critical. If it's not seated flat, the cylinder will tilt. So before we even touch the machine, pad goes into retainer, pad sits flat. Retainer is clean, no debris, no grit. Now it is time for a few questions. Why do we dust the pad sometimes? What is the first thing you do if you see grit stuck to the pad? Now we are at the actual test. Look at the load deformation curve. It shows an important point. With unbonded caps, you may see early cracking while the specimen is still carrying load. The slide gives a critical note. Do not stop the test here. In other words, if you hear a crack or see a small crack early, that does not mean the cylinder has reached peak load. The specimen can still climb to ultimate capacity. So what are the instructions? Align cylinder and bearing blocks. Apply load continuously until the cylinder is compressed beyond ultimate capacity. Ensure true failure is recorded. Technician focus points during loading. Cylinder centered. Retainers properly seated. Guard closed. Continuous loading. No stopping, no hesitation. This prevents underreporting strength due to premature stopping. Now, a few questions. If you hear cracking at mid-load, do you stop immediately? What could happen to reported strength if you stop too early? Pads are not permanent tools. Pads have a life cycle, and if we don't manage it, our results become unreliable. This slide shows a visual inspection guide. Acceptable perimeter scuffing can be acceptable. That means some wear around the edge is normal. Reject. Cracked or split pads must be rejected. If a pad is cracked, it will deform unevenly and can fail suddenly. Now the tracking rules. Maintenance of records is mandatory, and reuse limits 50 megapascal concrete, max
100 uses. 50 to 80 megapascal concrete, max 50 uses. So here is what I want in this lab. Every pad set has an ID. Every use is recorded. Every technician knows how to log the count. Pads are removed before they become a problem. Now, a few questions. Is a cracked pad ever acceptable if it's just a small crack? Why do we track reuse count instead of waiting for failure?
This slide is your decision tree. This is what protects your lab from using an unqualified system. It starts with the question, are you using standard neoprene pads? If no, qualification required, because non-standard materials must prove performance. If yes, next question. Is concrete strength 80 megapascals? If no, qualification required. High strength range requires qualification. If yes, next question. Are reuses within standard limits, 100/50? If yes, no qualification needed, standard use. If no, qualification required. So basically, non-standard pad equals qualify. High strength equals qualify. Excessive reuse equals qualify. Qualification is not punishment. Qualification is proof. Now, a few questions. If someone uses pads beyond 100 uses, what must happen next? If we switch pad brand, should we assume it's equivalent? Now let's discuss how qualification is actually done. This slide shows a statistical comparison between unbonded system average and bonded system average. The sample size requirement shown, minimum 10 pairs at highest anticipated strength, plus 10 pairs at lowest anticipated strength. So we are not just testing one cylinder. We are testing a meaningful set so we can prove consistency. The requirement shown is unbonded average must be greater equal 98% of the bonded average. That means the unbonded method cannot systematically underreport strength. And validation must pass a t-test at 95% confidence level. So what does this mean for technicians? It means qualification is a controlled comparison. Same concrete population. Two preparation methods. Compare results statistically. Confirm equivalency. Now it is time for a few questions. Why do we need both high-strength and low-strength pairs? What does 98% mean in real terms for reporting strength? Now we bring it all together in one checklist. This is the slide I would post on the wall next to the compression machine. Let's walk it. Strength, check. Concrete is between 10 and 80 megapascals, or system is qualified. Pad selection. Hardness, sure. A 50, 60, or 70 matches the strength range. Hardware check. Retainer dimensions and plainness are within tolerance. Specimen check. Cylinder ends are perpendicular within 0.5 degrees and no depressions greater than 5 millimeters. Safety check. Machine guards/enclosures are active. This checklist is how we prevent bad tests, bad breaks, and safety incidents. Now a few questions. Which checklist item do you think technicians skip most often? If one item fails, do we proceed anyway? Before we finish, let's make sure everyone uses the same language. This diagram defines specimen equals the concrete cylinder. Retainer equals the metal fixture, ring plus base, for support and alignment. Pad equals the unbonded elastomeric insert. Unbonded cap equals the combination of retainer plus pad. This matters because in lab communication, people say things like, grab the cap, or use the pad. And if the terminology is sloppy, mistakes happen. So I want you to be clear. The pad is not the cap. The retainer is not optional. The unbonded cap is the full assembly. A few questions for you guys. What two parts make up the unbonded cap? If someone hands you only a pad, what are you missing? This is the final slide, and this is where labs either stay compliant or fail audits. The slide shows a service record card with date in service, pad manufacturer, shore hardness, current reuse count, example 34 out of 50. The reporting requirement is clear. Test results must be reported as standard compressive strength, and records must be maintained for pad service life, pad hardness, reuse count. So when an auditor asks, "How do you know this pad was still within limits?" your answer should not be a guess. Your answer should be the record. This is also how you defend your results when a contractor disputes a break. Here are a few questions for you guys. If a pad has no record card, can we use it? Why does reuse tracking protect the lab legally?